you could all please take a seat, settle down. Welcome to the evening panel session here at Hot Chips. I'm Krste Asanovic from UC Berkeley, and I'll be the moderator. I just want to say, though, that the panel organization was a group effort between myself, Ralph Witt, the PC co-chair, and Chuck Moore from AMD, who helped put this whole thing together. So the theme we started thinking about was technology scaling at an inflection point. All of us thought technology scaling was hitting some kind of inflection point, but people tended to disagree on what exactly was inflecting, and if it was inflecting at all, and if so, who really cared? And if they did, what would be next? And so we pulled together a really great bunch of panelists tonight to share with you their thoughts on what they think is an inflection point, if any, and what they'll be doing differently, or what the industry should be doing differently in the future. So each of the panelists was told they have a few minutes, 3 minutes, to make their initial position, and then after that we'll be able to hopefully get a discussion going with questions from the audience. So first up, I'm delighted to have Brad McCredie from IBM. So he got all of his degrees from Illinois. He joined IBM in 1991 and was involved in many generations of power architecture. So he represents our big iron CPU guy. He's currently IBM Fellow and a VP for Power Technology at IBM.
Thanks, Professor Savage. Thanks for having me here. So we got an inflection point on technology. Well, that's kind of, it is a pretty well-worn discussion. I think the way I think of it is the inflection point happened somewhere around 90 nanometer, the first inflection point. We stopped thinning oxides. We haven't dropped the voltage much since then. So what happened at that inflection point? Well, at that inflection point, actually, I think what actually happened there is technologists finally had to earn their pay. Up until then, it was pretty easy. You went to Bob Denard's paper, got the recipe, thin an oxide, shorten the gate, and next thing you know, you had a twice as fast technology. Us designers, all we did was make a phone call, told them to write the same chip in the next technology, and it was twice as fast and half the power. But what changed after that is all of a sudden it became very expensive to do technology. And I think we've seen the fallout. I think you see that we stayed on a lot of that curve, but it just became a lot more expensive, and the guys that won had big wallets. And so now we're going on, and we've done that for quite a while. We've gotten most of our technology gains since that inflection point from a lot of hard work. I mean, we did strained silicon. You want to talk expensive, right? I think strained silicon, we were winding up atoms to get electrons through crystals faster, right? So that sounds pretty hard. You know, we did dual halo implants and all kinds of funky things to make technology go faster, and we spent a lot of money doing it. Now, the next inflection point, so what's next? What's next? We don't know, but maybe the thing that is going to happen next is we're going to transition from maybe a wallet-based competitiveness to an IP-based competitiveness. Maybe the guy that's going to win now is going to be the innovator. Because before, you had to be really clever and have $1 billion. Maybe if technology is going to start leveling out, which may very well happen, I think. You know, we just might have played most of our tricks, and manufacturing and the next fastest chip's not going to be it. Now it's going to be the guy that shows up with a bright idea. And we see a lot of that, right? You know, we got all kinds of accelerators out there. We got lots of clever designs out there. And the thing that's going to come is going to be the guy that has the bright idea how to take this technology that exists, and maybe everybody's got that same level playing field, and do something really clever with it. So I think that might be where we're heading next. I'll stop there.
Okay, so we have to get cleverer. Okay, next up is David Witt. Many of you will have seen his presentation earlier today on OMAP. David got his degree from Wisconsin, bachelor's degree from there, and he's been with TI since 2002, where he's been heavily involved in OMAP architecture. But previously, he did work as a CPU designer on the K5 and K7 at AMD.
Okay, so we had a choice of we could present foils or hand waves. So I got a couple of foils together, and I couldn't even get them over across on SneakerNet up here. So I'm going to hand wave. But from a what the hell to do with all the transistors you're going to go give us for free, from a wireless handsets perspective. For as far as I can see, there's no lack of innovation or something that actually has to be broken or enabled in software to allow us to build much more parallel systems than the OMAP4 that you saw today. The coming of 3D UIs, much better graphics, 120, 240 frames per second, 1080p encode and decode, and really good 3D audio, and moving to single precision. LTE doing 100 megabits per second through the air, gigabits per second through the air through wireless LAN. All these things just burn up transistors, and one thing I'd assure, I'll bet you any money, is everyone in this audience has one of these. Not necessarily, first probably right side up, not necessarily a BlackBerry, but handsets really drive billions of units, and the applications and the things that people want to coalesce around them aren't stopping. So from that point of view, an inflection point, well, I don't see one in terms of what the hell am I going to do with the transistors. If you're into standard CPUs, maybe you're at some point, geez, I stepped and repeated 4, 6, 8, 12, 128 processors, and what the hell am I going to do with all these general purpose processors? But in handsets, and handsets in combination with wireless applications, it's just not true. However, Brad had a very interesting comment, so I'll relay it. And that's chip companies don't make money, and so one of the problems was, it's something that we can architect and build and find great use for this, but it's not just the hardware, the technology. There's a fair amount of software and system necessary to build these things. Actually, an almost crazy amount to hit those type of applications that you're seeing today. And so the cost of that and the cost of the process technology, and especially some of the leapfrog techniques that we're going to be looking at, such as through silicon via 3D stacking of memories, et cetera, and the assumption that all those additional things that we're putting together are going to require every 2 or 3 years a 2x increase in the number of transistors we can put down. At some point, that's going to be very, very hard, and very few people are going to make lots of money or any money in I suppose what's my chosen field right now. So who pays for it all is really a question, because there's really only going to be a couple of winners in handsets able to afford all of the many costs associated both from the process technology and then the software and system. So if we're looking for an inflection point in handsets, I think it's kind of everything, as this is how complex this is to keep on this treadmill. Thanks.
Okay, thanks, David. So next up, we have another application area, which is FPGAs. And we have Michael Hart from Xilinx. He got his PhD from Southampton in the UK. He spent 25 years working in the semiconductor industry, and now he's responsible for advanced process technology at Xilinx.
Good evening. Hope you can all hear me. Let's see. I have a few viewfiles, so go through these quickly as I can. In general, I'd say technology inflection point has been spoken about, the 90 nanometer case, but beyond that, looking forward, things look pretty good. Technology scaling continues. It's been 45 years since the original formulation of Moore's law, and we're still moving. 2-year cycle of Moore's law seems to be self-fulfilling. Industry is still moving to 32 nanometers and beyond. Semiconductors have become pervasive throughout society, $250 billion revenue last year. And we have many, many products now with more than 1 billion transistors. So, you can see that from the early 70s till today, cell phones have improved in size slightly and functionality, and the video game machine has certainly changed from the 1971 model here. There's some warning signs for the future. Certainly the cost of technology scaling is increasing every generation. And, the industry is moving pretty much to the fabless foundry model. and we're seeing continuing consolidation in that model. The costs are beyond the reach for most people, most companies. You know, people are talking about $60 billion development cost for a typical ASIC at 45 nanometer. And so those ASIC designs are somewhat disappearing, except for a few high-volume products. You know, the big enabler for scaling has always been lithography, and that's definitely under severe pressure. Next generation platforms are not viable yet, although one of my colleagues here will certainly be talking to you about the future potentialities there. And, you know, we are certainly reaching the limits of the MOSFET. I don't think we're quite there yet, but certainly, you know, many discussions are around power, performance, and headroom, and so on. So looking forward, technology scaling will continue for many years. I think there's always a doom and disaster about 2 generations out. The sky's falling, but it's been 2 generations out for maybe 30 years. So hopefully it'll continue that way. Lithography solutions are in development, and meanwhile there are ways around this for the short term. And one thing that the design members of this audience must realize that there is no numerical device yet. You know, there are some devices demonstrated, maybe Mark will talk about these, to beat the fundamental KT over Q, but they're not ready for prime time. So you're going to have to live with the MOSFET. It may be leaky, but it's still got an on-off ratio of more than 1 million, which is a pretty good switch. Okay. There's only going to be a few companies moving ahead with advanced technology. I think, you know, we just saw a report in the last week of only 3 companies this year spending more than $1 billion in CapEx. Programmable imperative is a phrase that you've probably heard. Coming from the FPGA background, this is definitely something that we're happy to see, but it is a reality of the industry that ASIC starts are moving away and people are building FPGAs driven by business conditions and also enabled by the increased capability of FPGAs. More, I think it's not being talked about much here, but the 3D integration, again, will be talked about shortly, so I'll move on. You know, there's a few things as a designer I believe you should be worrying about. You know, first-time design is probably top of your list, but there's things that are making that very difficult, and those aren't going to go away, so keep trying it. I had just one rather cryptic last page, which is, you know, if the Moore's law, which was originally a year, and then became 18 months, and then became 2 years, if instead of saying that, if we'd have said at the beginning, why not go follow a 3-year cycle, then, you know, we'd be looking at quarter-micron technology today, and a lot of the pain and suffering that maybe some people are feeling would be not there yet. And biggest chip would be a Pentium 3, 10 million transistors. It seems very small today. So you wouldn't be worrying so much about scaling, power, variability, etc. But, you know, at the same time, what would you have? You'd have a Nintendo 64 that your kids would be playing with, and a Nokia cell phone that still makes good cell phone calls, but wouldn't do a lot of the other wonderful things. So just to conclude, I'd say, you know, I don't really see a technical inflection point for the next 5 to 10 years in fundamentals, but perhaps there will be a financial business one because only a few companies can afford to continue. Thank you.
So we're going to switch gears a little. So our next panelist is Lode Lauwers, and he's a process technologist. He works at IMEC, and he joined IMEC in 1985, and he's currently the Senior Director of Business and Partner Relations at IMEC.
So good evening. I also brought a few slides, all from Europe. It was not so heavy. I'm happy to see a lot of positive comments about not too big inflection points in the future. If you see over the past decades, we have continuously been tackling more and more research challenges. This is like the number of technologies of materials we have been worked on in R&D in the past decades. You see, it's always been increasing. Also for the next, so this decade, it's increasing, and it's still there on the list for the next 10 years. If we see at the litho side, which is like the key enabler to decrease the cost per function, we have like 2 main technologies we're working on. One, immersion lithography, which is becoming mainstream. We are doing there a lot of double patterning techniques, so still a lot of gain to be expected there. But our big faith is in EUV. Say, yes, it's a critical technology, the equipment is still there to be developed, so it still takes a few years, but we are very confident it will be there, and it will enable a lot of further scaling at the litho side. At the other side, okay, in terms of keeping up with performance, if we see in the past years, a lot of techniques have become mainstream in our technologies that you're using right now. Currently, we're focusing at like everything at 22 nanometer and beyond. So 15 nanometer, 16, 15 nanometer as like main target. What is available there? What can we target there? We have technologies like germanium 3.5 technology, graphene as various types of materials, nanowires, tunnel FETs as alternative devices. One of the major technologies we're working on right now is the germanium in the channel to enhance mobility and to offer more and faster devices. The interesting thing is that you can make it on islands on a chip with selectively deposit germanium, so that that you can be very flexible in making an attractive chip. So that's all for like the 15 nanometer. This is kind of the dashboard, what we are looking at in terms of say 5 years from now. And you see for SRAM, we're also having a memory program for DRAM, for non-volatile. So in terms of SRAM, we really, and the logic, we really believe in these 3.5 channels. So high mobility materials, so germanium and 3.5. Germanium, we have a very good PMOS already, NMOS unlikely because of leakage, but 3.5, we have the materials there, so we think we might be able to come up with a high performance CMOS germanium 3.5 combination. Floating body RAM is there for as a potential alternative. Other device structures we're not so sure of. In the DRAM, very high K materials for capacitors like K above 80 to 100. We're simulating K materials. Oops, that's 3 minutes. Ruthenium as very dirty and aggressive materials, but still there, it's on the roadmap. And resistive RAM. A lot of people are interested there. Programs are increasing everywhere. And then possibly, but let's say more uncertain, is like probe memory, graphene, MOD transistors as alternative techniques. Of course, at the interconnect side, not so much there on the roadmap. We have the generations of low K, but that's saturating around like K 2.2 or 2.0. If you go below, your materials become too porous, so it loses strength. So that's not a target. So people are working on air gaps, but like our major faith there is 3D technologies. So I have a special slide there that, okay, you can do 3D in various kinds of areas of the technology, but like we have two major technology roadmaps for 3D. One is the 3D stacked ICs, where you have like vias at the metal 1 level. You can make them very dense, high aspect ratio, but very dense, and you have the remainder of your interconnect still available for your chip interconnect. On the other side, you have like more like a stacking technique with less dense vias, but you can do them post-foundry. So, and both techniques we are developing, both techniques we see very high interest from system companies. So there we have a lot of in-between results. Still, we need, of course, to come up with a very cost-efficient process so that it really can be an alternative when you start designing a chip. So what we see, at least, is that an institute like us, we feel the need that there is an increasing need to build links between like the designers, like the IC companies, but also those who went fabless or fab light, and to keep the link with technology. So to keep the link with all these developments of materials, so you need to involve the software suppliers. For instance, if you talk to 3D, like how to link with the tool suppliers in order to have a 3D design flow. All these things, that's what we need to do. On top of that, there is what we call the heterogeneous integration. that's beyond CMOS or the above CMOS, whatever you like. We believe that advanced CMOS will always be there, but on top of that, we'll be able to build much more functionality. We're doing that right now. That can be mechanical, the MEMS. You can have a lot of ideas to make advanced sensors, actuators, interconnect biomolecules or sensors for biomaterials on your chip. Photonics was mentioned today, thermal sensors, and so on. So these things, this might be offering, so there is no inflection point in terms of technology. We'll still have a lot of things for following the Moore's law. On top of that, there is the potential to combine your chips with additional functionality with all these new functions. Okay, that's it.
Thank you. And finally, we have Mark Horowitz, who probably needs little introduction to the crowd here. So Mark Horowitz is a professor here at Stanford. He got his PhD here in 1984, and I guess he decided to stay. And he's probably going to say something completely different from the rest of the panel. So.
Thanks, Krste. Yeah, I will. So we've heard a number of people come up to the panel and say, either, well, there may be one a little bit, but it's not that important, or I don't see really an inflection point at all. My perspective is that we're at an inflection point. You better believe it. I think most of the world's in denial about it, and I don't think that's healthy for this industry. So one of the things that previous Brad mentioned, and certainly the case, is that fabs are getting much more complicated. The capital expenditures in building a modern fab are extremely large, and as a result, the number of people who are building fabs and developing new technologies are decreasing rapidly. I think we were talking on the panel, and we think there are like 3 major people investing in new technology. So one thing that you might say is that, well, that's a big change. I'm not actually worried about that. I mean, I was involved with a company that did contract business with a lot of different foundries when they all existed, and we got all their very hush-hush proprietary technologies, and they all were different, but they all were the same. You know, CMOS at a particular generation pretty much looked similar because people solved the same problems. I think consolidation in that business makes sense. Maybe that's because I'm a designer and I'm not a device technologist, but I do think that, at least in very advanced CMOS technologies, the physics constraints are getting more and more serious. You're doing more and more similar things. It makes sense to have fewer people do that. That doesn't worry me. I don't think that's going to change technology. As long as there's some place that can actually fab my wafers, I'm perfectly okay with that. So what is it that I think is really at the transition? I think there are 2 things that have fundamentally changed, and we better wake up to it. The first is that while we'll continue to scale technology, I agree that Moore's law hasn't stopped. The benefits that we assume we get in technology in terms of the energetics of the devices and the improved performance of the transistors are no longer true. We have been, by Herculean effort, been improving transistor performance by adding all these special sauces. And all that reminds me of is my early days as a bipolar designer, where every generation you got faster bipolar transistors, at least a little bit by magic. But that magic kind of wore out after a while, and CMOS took over because it had a much clearer scaling path. You didn't have to redesign your circuits on every generation to get higher performance. I think the performance is not scaling, and I think more problematic than that is the fact that energy is not scaling. And everybody's assuming we're going to develop these technologies that are going to be able to do more computing. Everybody wants what's on their desktop and their handheld. We're talking about doing all this stuff. It ain't going to happen unless we figure out much more efficient ways to do the computing, because the technology by itself is not going to do it for us anymore. We want to build ever more powerful machines. We're going to have to make them more efficient, and scaling's not going to do it. And that's different, and that's the first takeaway where I think we're at an inflection. The second inflection point, I think, was also mentioned, and I forget who mentioned it, is the cost of doing design today is increasing at a rapid rate. I used to say that ASICs cost $20 million. I think I saw $60 million here, so whatever, it's a big number. The number of people who can actually do application-specific circuits is decreasing to 0. There are no application-specific circuits being built today. They're all standard products. Everybody who builds a chip has to sell them to lots of people to recoup their investment. That's bad. It reminds me of what happened here, what was it, 30 years ago, about 25 years ago, at the beginning of the ASIC revolution. Probably many of you people aren't old enough, but there was a period of time where technology was incredibly capable and it cost way too much to design because everybody was designing full custom chips. And all of a sudden, synthesis came around, Verilog came around, and we had a whole new way of designing chips. If we don't do something soon, we're not going to be able to we're not going to enable people to think of the clever solutions and implement them because no one's going to be able to come up with the capital expenses to do that. So we need to fix that problem, probably more important than anything else. Otherwise, we're not going to scale technology moving forward. Thank you very much.
So I urge you to think of questions and get up to the microphones in the aisle and state your name and affiliation before asking a question. Just to get going, I might just throw another thing into the panel following on from Mark's comment. So cost was mentioned by everybody. So how do panelists see this splitting out? Will any big systems company justify having a fab?
Sure. I mean, Samsung's not going to get rid of their fabs, nor is Intel.
I mean, somebody whose primary business isn't building silicon, I'll say IBM. I'm looking at Brad, I guess.
It's going to become a flat playing field. I mean, the technology's not scaling. You know, so you're going to walk up, you're going to look at your next computer, and you're going to say, I'm going to spend X number of dollars. I mean, that's ultimately what Mark said, and that's what I was trying to say. Eventually, you're just going to look and say, where do I put my $5 down that I get the most return on investment? And you can do some of the things on the charts that were shown up there. None of it was technology scaling on the charts. Everything up there was just a trick. I can put a different branch prediction into my design, and that cost me $5. Or I can do another halo implant, or maybe another strain on the silicon, and that cost me $10. But that's going to be the economics that we go through. You know, we can invent a new technology trick, we can invent a new design trick. I think the inflection point is, and I think it really is a strong inflection point, is that 10 years ago, 15 years ago, it was pretty straightforward. You got more ROI for your buck spent on technology development. Now, it's a thoughtful decision each step of the way, and you got to think it through. I don't think technology development or investment's going to zero. I don't think we're going to dump all the fabs. I don't think we're going to dump our fab. You know, I think we're going to keep doing it because you can still differentiate with technology. You can still get leadership with it. But it's just a different game, and you have to think it through, and it's a much more thoughtful process. You got to earn your paycheck. You got to be clever. So it's not going to be a simple straight line. It never is. No tree grows straight to heaven. But their fab innovation will be part of the equation going forward. Design innovation is going to become a bigger part of the equation, and that's the inflection point you got to get over.
So I also think one thing that we should keep in mind is that we shouldn't equate high-end silicon technology, CMOS technology, with fabs. You know, the sobering thought is that people spend more money for the switches, you know, in a power station. You know, if you have a solar system, the power station that you put on the side of your house, you spend more money for the transistors that just turn on and off to basically switch the high voltage efficiently than you do for the microcontroller that has 40 bazillion transistors on it and calculates everything for you, right? So somebody is making a lot of money making semiconductors. Okay, so lots of companies are trying to figure out how to get into other businesses. The more than more is really interesting because you can basically build lots of interesting products by attaching intelligence to other things. And that's where a lot of value is going to be created. Right.
Okay, so on that, so do you think teaching students as a professor? So what I should be teaching? What you're telling me is the main skill I should be teaching is how to design hardware. Like, forget about, you know, this is the growth industry is really good quality design.
Yeah, I think you're going to have to innovate, and the guy that's going to come up with, you know, I think it's going to flatten the playing field. I really do. I mean, the raw manufacturing aspect is going to be de-emphasized. The raw scaling aspect it is gone, and now you're going to have to innovate to make money. And a lot of that innovation, a lot more of the innovation is design. It's going to be, think of a new accelerator, think of a new thing. You may see more. Right now we've seen a weeding out of chip design companies, especially in the high-end microprocessor business. You may see more of it now, because now the field's going to open up again. Before, you had to have $1 billion to go play, and that weeded a lot of people out. But now, there's going to be a lot more room to design. There's going to be a lot more people to design. There's going to be more specialized stuff out there from a high-end microprocessor perspective.
And maybe I would also like to add, if there were to be an inflection point from an economical perspective, I think you say it's different than in the past. Maybe right now a decision will indeed be taken more thoughtfully, in the sense that up to now we almost had like a common roadmap. There was some timing difference, but essentially technology-wise it was an almost common roadmap. If you look at the economics of certain technologies, equipment, investments, you may expect this will not be the case in the future. Depending on your markets and whatever you make, like you may want to follow certain technology trends or not. So there will surely be more differentiation in the future than, and less commonality between the roadmaps.
I'm not sure I agree with that, actually. I think that the foundry model is driving a lot of commonality in technology, and also the fact that the number of equipment suppliers has come down to a very small number. And therefore, as I think was said before, that by Mark, the technologies actually have looked very similar. A CMOS technology in one fab looks like a CMOS technology in another. Now, maybe what you're referring to is the 3D and the more than more, where you can bolt on things onto the base CMOS. But I think the base CMOS will look very similar. And then, whether it's 2 companies, 3 companies, 4 companies, it doesn't really matter that much. You have to differentiate in your design and in your software and in your product features beyond the base technology.
Okay. Question from the audience?
Yeah, Russ Tuck. I'm at Google, but I used to work for some system companies. Question for Mark. When do you think we'll get down to fewer than 3 foundries? I would think that's an inflection point as a customer. If you have more than 3 foundries, it may not matter, but if you have less than 3, it starts to matter a lot.
Was that a question to me?
Well, you were the one that says there were still plenty. When do you think when will we get down to less than 3?
I've worked in this foundry side of the business, the fabless side of the foundry business for many years. It's very unpredictable. I think if you look back in the last 5 years, I mean, the trend is definitely to a smaller number, but we have a case where Samsung came onto the scene just 2 or 3 years ago, and they were doing some foundry work in the past, but it wasn't leading edge technology. But they joined the IBM ISDA alliance. Just 6 months ago, the fab side of AMD received a huge cash infusion, has now become Global Foundries. So, it's not a straight line deterioration in the number of foundries, but so I wouldn't like to say when it's less than 3. Maybe 10 years from now, I could say that would be the case.
So just from pure economic terms, I think you will always have more than 1. Maybe 3 is a reasonable number, and that if it ever falls below that number, there's a sufficient volume in the business that if people want the extra number, that will happen. Some country will decide to do that investment, right? So in terms of people developing technologies, right now it's primarily driven by IBM Alliance, TSMC, and Intel do technology. But there are other Taiwanese foundries, UMC, right? And there's still many players. So I'm not too worried right now.
Okay. I have another question, if it's okay. The comment about ASICs being more and more expensive to design. It seems to me that one of the leading things with ASICs was that you really had to squeeze the computing power on to fit what you could do with the I/O, and that it seems like the square law that we're more I/O constrained than logic constrained. At some point, it may be that software on a sea of cores will be sufficient. Do you think that's true, and when?
So that's actually one of the big questions I think that people are debating, and I think my view of it is it all comes down to energy efficiency. By building customized hardware for applications, you get much higher energy efficiency, orders of magnitude, probably 2. So to the extent that that doesn't matter, I think you will do uniform Cs of processors or programmable platforms in some ways. And the real question is, does energy efficiency trump that in certain applications where you have to do some customization? And I think if we don't do something for the design problem, that bar is going to be pretty high. But I actually think the field, just like it was 25 years ago, is ripe for an innovation. That is, if you think about the hardware we build, it's not that different than the hardware we built last time, right? You use processors and you have, addition. There's not that much stuff we know how to do. So why don't we make it easier for an application developer to actually create a piece of silicon by maybe just customizing one of these configurable platforms in some way? I think there's a way that we could make this much easier. And if we did that, then we'll see if there's a market for it.
Well, the next speaker comes up. I just want to direct a related comment to Michael about FPGA. So if Mark is successful and makes design incredibly cheap, and technology stops at some design node, do FPGAs cease to be competitive or an interesting market?
Well, FPGAs are still in the mode where we gain from each generation of technology advantage. So that's a positive. But yes, will that come to a stop? I think there's a few companies that are still going to drive technology because there's a financial reward for it. And FPGAs still fit in that category. So, we can't do it alone, but with a few other companies like us, we can do it.
Yeah, Danny Cohen from Sun Microsystems. We are in the middle or beginning of the end of information revolution, which was enabled by the technology. And the revolution is not the technology, but really more the application, from Twitter, to email, and all of those things. Now, technology, part of what took the technology to where it was the education, that we were able to educate thousands of designers, out of which some of them succeeded and pushed bigger things. And the universities, Mark in Stanford was, I think, on the MIPS project, and Jim Clark has a geometry engine, and Peterson have the RISC machine. And there were lots of other machines that came from universities, none of which had $1 billion, as the gentleman in the yellow shirt suggested. Excuse me for not remembering your name. Yeah, but it was possible. It was possible to do it in universities, and now it is much, much more difficult. So my question is, shall we start in making it easier again?
Do you want to take that, Krste?
No, we're working on it. Yeah.
Go ahead.
Go ahead. So it's been very expensive to build chips and very difficult in universities, but some of us still do it. I think some people in universities are overambitious about what they attempted to do, and that led to some, not so big successes that kind of quietly that corner of the university business died down. However, I think there's always a new generation that are young enough to forget and try again. And I think there's boundless energy. Like, students just want to build stuff. I don't think you can try and stop them, but they just want to build stuff. And I think we'll figure out how to make them be able to build stuff.
So Dan, I completely agree with you, but I think in some ways our focus on chips is misdirected. What we want to do, I believe today, and I think that the issue that's going to, if the industry is maturing, if technology is maturing, it's all about mapping applications to solutions, right? There are tons of incredibly powerful chips out. The OMAP processor, right? You can buy it for $20 or something. You can buy a whole Unix board for $100, right? The point is that we can put in the hands of our students tools and technologies for them to build hardware systems that they couldn't imagine that they could build. It's like walking into a software class, and at the end of the software class, you write a program to something you never imagined you could build. What we need to do is create the equivalent class for building a little embedded system with hardware and show people how to do it. And I think if we did that, we could walk a long way to accomplishing what you want.
Yeah, that's a great point. Chip design, right? I mean, and you actually see this in the industry too. Chip design has evolved. It's a very highly refined art now, and it is an art. I mean, 10, 20, 30 years ago, it wasn't a refined art. Now, you got companies that have 20 to 30 years of tribal knowledge of building chips. And frankly, it's one of the biggest challenges. You're from Sun, so maybe I'll even take a poke at you. I mean, once you forget the recipe, it's hard to get it back. I mean, and it's really true. Once you fall off that merry-go-round and you lose a whole generation, it's hard to get back on, let alone get 20 grad students to go and do a chip. Now, when Patterson was doing the first RISC chip, it was a lot different. Even within IBM or within Sun or within any other company, right, we were all writing little shell scripts to figure out how to wire up transistors and doing it all with rulers. I mean, when I was in grad school, I was going and doing my internships at Intel and measuring wires with a ruler. You can get grad students to do that. But now it takes, an incredible software stack, and it's different. But what Mark pointed to is the spot to innovate now. The spot to innovate is this higher up the stack. And that's what the grad students should be doing right now, is they should go ahead and take these wonderful works of art of these chips that we build and take them and figure out new ways to hook them up, program them up, and do something that couldn't be done before.
To do that, you don't need the $1 billion that you suggested before. And what we really need to see is people like Mark, that luckily are in the education business, pushing that right thing.
I would not go play in that pretty well-tried ground. I would go find a new pond to play in. Absolutely.
Thank you.
So just by the way, for those of you that aren't aware, because actually $60 million in some cases actually is relatively cheap for a new development. But
how much did you spend on the
no comment. But
I didn't know we were doing confession up here.
Yeah. But it's kind of funny that if you're doing high-end processors or these massive but inexpensive application processors, but you spend a couple of years basically in a virtual world of simulating, modeling, and verifying these things. But you basically are placing a bet that first silicon is basically close enough to perfect that you can take that and move it to production. So it's really kind of yes, we have the formulas all down, but there's a tremendous amount of software and individuals behind making this work. If first silicon of several hundred million transistors isn't perfect, we're all dead. You really don't get a second chance. Even mass sets. We didn't actually talk about how expensive, but mass sets $2 million, running 24 a lot through is probably a couple $1 million. And it takes a couple months to move through a fab. So if you don't get it where it's virtually perfect on the first rev, you're already dead. So this is not something that it's interesting to exploring and exposed to graduate students, but it's definitely something that it's only for the select few.
Well, I wouldn't go that far. My students taped out a chip, we got it back, and it worked. We didn't do it the speed that maybe you guys would do it, but
But I think there's, the other way to look at this is, as a student, you don't necessarily want to be designing at the gate level, right? You want to be designing at the system level, and there are great development boards out there on, like the OMAP or FPGAs or microprocessors, and you can build the whole system, and you can, you never even need to know what a semiconductor devices anymore. And I'm sure a lot of students in the universities don't at this point, because they're working at the software level or at the high-level extraction level.
So I didn't mean that as a denigration comment. Anyone wants to go off and do chip design, feel free. But actually to find something that you can drive, hundreds of millions of units, because that's what we have to do with very, very few defects. And all kind of the technology we were just talking about before, it just becomes very, very hard. So it's not so much the transistors or actually the accelerators, it's really getting it all and the system and software on top of it to work. It's just difficult.
Krste?
Aaron Partridge, SciTime. I'm concerned about another inflection point, and that's an inflection point of startup companies. 5 years ago, a couple of guys and I had a cool idea. We went up to Sand Hill Road, we got it funded, and now we have a startup. And unfortunately, that's getting very hard to do. What's going on is now it takes $50 to $100 million to get a chip out the door and to get it into a customer system. And that chip had better be a blockbuster, because company valuations are small. So that means it's got to go everywhere. That means it's got to be a general purpose chip that everybody wants. Well, that's kind of a hard thing to do for a couple of guys with a couple of $1 million. And the VCs are shying away from this model, rightly so, I think. It's getting very hard to start up a company doing high-end chip designs. And I think a lot of the people in this room sort of got a lot of the new technology going under that kind of a condition, a startup company condition. I don't see that going forward. What are we going to do to replace that engine?
Move to energy.
Energy, we make single transistors that are about 8 inches on
But
the
if you want to start a company, it works pretty well.
So, just to answer that, I think from my perspective, what that means is that, to design a chip, as you say, costs so much money that a small startup company will not get funded. But they can be funded if they use a platform device from another manufacturer to build a product. And they build their own level of IP on top of that. So there is still funding for that model of company. But if you really want to get your hands dirty and design a real IC, it's very tough.
Yeah, I think starting from scratch, that's rare, right? There will be more and more IP out, or just the investment is too high. But you can start from certain thing, and what you think also, what we see, that you have certain projects that are embryonical, and you keep them, for instance, in an institute somewhat longer, that it gets some scale, and then you help it to go to the market. So you need, like, if it's too early, it dies because it doesn't get the investment. If you wait a little bit and you help, then it becomes a little bit more mature, then the leap towards a full private investment is a little bit easier. So that's also a solution.
So I'll take a different view. I'll try and paint a different picture for you. Suppose all the stuff on Lode's chart doesn't come to pass, and we run out of all these clever ideas because it's not scaling, right? Technology's not scaling. It's trick after trick after trick, and maybe there's a finite number of tricks. Maybe 22 nanometers is going to be the last set of tricks, maybe 15. But let's say that comes to pass, and let's say technology nodes last much, much longer. Okay? If we stay in a technology node, and in a halfway competitive technology node for your clever startup idea, is 5 years old. Now I bet it's really cheap to RID into it. I bet it's really cheap to get a tool set for it, and I bet there's a ton of the run-of-the-mill IP out there for you. There'll be 53 PCI Express macros for you to choose from, and 48 differential high-speed interface links for you to choose from, and it may be really cheap for you to put your clever idea onto a silicon and get it out there, because now you're not going to have to pay all that premium to get that new technology. And that may happen. That's what I was talking about, that we are at an inflection point, and maybe it's going to go back the other way. Maybe it's wishful thinking on my part, but I would argue that if we stay in technology nodes longer, and all those, we don't stay on that grind, and we start stretching out these technology nodes, it may get cheaper for more people to bring clever design ideas to market. And that might reinvigorate some of the things you might want to do.
Oh, sorry, Mark, go ahead.
No, so I want to say two comments. One is, that kind of thing is already happening. If you look at just design starts, not all of them are actually in the most advanced technologies. If you listen to the conference, there are a number of people who actually are doing things that instill 130 nanometer kinds of technologies, because it's very cheap to do the tools and difficulty is less high. But I would say that if you want to do those kinds of things, we need to basically do another generation of design tools or design methodology, the way we approach design, that up-levels it, so we are sticking together the kinds of library elements that are available in a way that the person who understands the application, right, can do it. Because ASICs were all about having applications people build the chip, because they knew what problem they needed to solve. Over the years, we have expert teams building ASICs because they're so complicated. Okay. This is broken.
So we're, in the last few minutes, we've been thinking about it technologically, but I think I'm directing us to think about it from a business model perspective. In other words, if I were to start a drug company now, I know I wouldn't get anything into human applications for 15, maybe 20 years. Yeah. And so the business model that the drug companies have taken is that when they have a startup, they tuck it under the wing of an established company that has a very long view. Startup companies in that space, in bio, can't freestand. And I think we might need to look at different models in the electronics side. That's kind of where I'm going.
Well, I heard a talk from somebody at a bio startup, Genentech, and talking about how they do that. And those stories are not that, I mean, I wouldn't use that as an environment we want to move to.
I agree.
Don?
So I'm Don Draper from True Circuits, and I'd like to address a question to the panelists. Of the $60 million it takes to develop a new chip, what portion of that is actually driven by advanced nodes, 40, 28, 22 nanometer, and so on? And what proportion is driven by the fact that chips are 2 times bigger, 4 times bigger, they've got vastly more logic on them, the logic development and the logic verification is getting increasingly expensive. The proportion of that chip that's driven by the actual advanced technology node, I don't think is getting as expensive as that. And the other point is, why are we going to these new technologies? It's because with enough volume, the cost per function is less. Although the chips are bigger, they include much more functionality than before. Anybody could comment on that? I would say one more comment is this leads to an increasing need for reuse, as I think has been commented on already.
Yes, so.
I think it's a good point, but when you get into that $60 million, I think a little bit of it is, and that's why I use the term stretching out the nodes, because when you get to that $60 million, actually I think 60 seems a bit high, but anyhow, that large number, there's a good hunk of it that is no matter how you slice it, when you're turning it over in 2 years, you're inventing a lot of stuff every time you go. And that invention is what cost. And that's why I use the example of all the IP reuse. No matter what, every time I see a chip that's an ASIC, there's always some macro that's not in the right technology, doesn't have the right interfaces, and you got to go pay to develop it. Now, if we spend longer periods of time in those nodes, you will see that number drop. So there is a piece of it that I think there's a time constant that you can plot, and I think Mark's example is true. You do see more and more people, messing around in 90 nanometer right now. Why is that? Because 45 nanometer is not that much faster than 90 nanometer, and you're only left with the integration value. So I think you will, if the nodes stretch out, I think you'll see the cost of development drop. Yes, sim and verification and writing the logic is still a big hunk of the bill, but I'll call it 50%. You're still, if your technology driving is at least 50%, I'll call that out.
So I'll respectfully disagree. So at least for us, we use the node for density, and so most of the accelerators that we build for video, graphics, image, display, audio, I mean, they run at 100, 200, maybe max 266 megahertz. So there's inherent parallelism there. You just need lots of gates and lots of memory. So for us in building application processors, it's not clock. It's not so much the entitlement of what the process gives. It's managing the new functionality as a massive number of gates and memory, and then managing the leakage.
So if 3D was free right now, you would go ahead and design all your chips in 90 nanometer and stack them up.
Yes, absolutely. Yeah.
Why would you do that? Because it'd be a lot cheaper.
Yeah.
So we agree.
Yeah.
If you stay in an old node that has all the pieces, you're good.
But for us in 45 nanometers, I don't see the technology. That's kind of my point, is that we have tools and that are good enough for doing on-chip variation. The other things you see are we write rules and what we can do and what we can't do in libraries and memories that basically abstract the node from us. Our designs are dominant in modeling and verification and new RTL. They're not in circuit design or obscure races or anything that actually is problems in the technology itself.
Maybe I give the perspective from the FPGA viewpoint. It's a little different, which is that there is a driving force to take FPGAs to the next technology node because 45 nanometer, the product is a quarter of the size of the 90 nanometer product, right? So, and when you talk about cost, we're not just talking about area, we talk about defect density, so it's a multiplying effect, right? So especially on a large chip, if you're building a 500 square millimeter die, it's going to be a lot more viable in a 45 nanometer technology, and you couldn't even build that in a 90 nanometer technology, right?
3D for free.
So, so 3D, but 3D is still not free because you're still going to pay for every wafer that you stack, right? So if you stack 8 wafers, you got to pay for 8 wafers. So the wafer has to be free, means that the wafer is going to be 1/8 of the price. No, that doesn't make sense, right? Today, unless the price of technology per node goes up significantly more than it is today, we're never going to get to the mode where that stacking is economically viable for big die.
I think it'll always be the case if I have X gates and I build it in technology A or build it in the scale technology, building it in the scale technology should be cheaper if you sell it in the volume. Yeah. If that stops being true, then scaling will stop. Yeah. But so far that hasn't stopped.
So the price per generation may be going up by more than the traditional percentage, but it's still not breaking that model. So, but then in terms of the cost of development, coming back to the $60 million question, where does that money go? I think, you look at the chips that are built today, they have a lot more functionality, a lot of high-speed SerDes, a lot of analog functionality, a lot of embedded memories. Those all take pretty big design teams, and, people cost money. So that's where a lot of the money goes. Definitely mask sets are more expensive. The silicon NRE, when you're running 12-inch wafers in a fab, costs more than it did when it was a 6-inch wafer. But that's not the big piece of the money, I don't think.
But the inflection point's here. I think the key point is we're talking about an inflection point. And I'm a packaging guy for way back, and I can dust off more pitches that I've put together to leverage IBM's MCM technology. It says, take that one big chip, break it into 2 chips, and we'll do 2 half the size chips and put them on an MCM, and life will be cheaper. The key point is that the value prop of the next technology is dropping more and more. And I'll go ahead and put it out there. You're going to see more MCMs even in high-speed microprocessors. You're going to see more DCMs where people are going to break them in 2 because that equation is starting to tip. It's starting to tip. And 3D may tip it even more. And that's the point. It's actually a debate now. 5 years ago, what you said, Mark, was absolutely true. And you're always better off on the next single chip pointer. It's not completely clear anymore because you don't get that 30-40% voltage drop. You don't get that 2x transistor. Now you're just talking density. Well, there's a lot of cheap ways people are innovating out there to get to density that it doesn't require $1 billion fab. So you got to think. It's a decision now. It wasn't a decision 5 years ago. It's a decision now.
Yes. Eliezer Rosenhaus, KLA Tencor. One of the advantages of having scaling is that it gives the system predictability. So it gives us, the equipment manufacturers, the ability to pre-design equipment to focus on a particular node that's coming. If we go to the model that Brad was suggesting, where you have all of these special innovative tricks that give somebody in particular an advantage, that removes the predictability, so it removes it increases the lead time that we have to produce equipment, and frankly, it may even remove our ability to build a coherent argument to our management that it's worth building a particular piece of equipment because we won't be able to amortize it among a large number of consumers or clients. How do you address that? I mean, it makes our life pretty difficult.
But you're doing it now. I mean, we're done scaling, guys. I don't know why we keep got all these charts that have all this scaling stuff going on. We quit scaling at 90 nanometer. we've been playing tricks since 90 nanometer. The only thing we've done is we've agreed upon the tricks. You know, we got agreed upon tricks. We got agreed upon metal gate. We got agreed upon strained silicon. So your only argument is did we agree on all the tricks together or not? That's the only point. But we're done scaling, and we've been playing tricks since 90 nanometer and finding other ways to get performance, other ways to get things other than scaling. So the only question is can the industry survive if we don't all agree upon the same tricks to play?
Yes, that is a question.
That's a good question. Will semiconductors become a competitive weapon, and company A do one set of tricks and company B do a different set of tricks and innovate and win that way? Or will it be that we all have to agree upon the same tricks and do the same thing and go? Because I think you'll see a few tricks. I think there might be some competitive advantage, but it probably won't be as strong, and that's why I think the inflection point is we're going to have to put those tricks in the design. It's going to be very, very hard to put them into the technology.
Still some comment though that it's not always tricks, right? If you see, for instance, the high-K metal gate as an example, it's not a trick, right? It's a solution. There was a kind of saturation. You find something new. I don't agree to call this a trick. Right?
Well, it's not scaling. It ain't scaling. I got Bob Denard's paper. Bob Denard defined what scaling was. We ain't doing that. So you can call it tricks, you can call it solutions, but it's not scaling. So all those charts you got that say scaling going off the top right, it ain't true. It ain't scaling.
I respectfully disagree there because the metal gate high-K, and I was going to say the same thing here.
High-K metal gate is another trick that's going to be good for a few nanometers, but it ain't going to take us to scaling.
But if you look at Denard's scaling law, 1 over lambda, the T inversion, the oxide thickness is fundamentally the enabler of scaling. That's exactly what metal gate high-K does. And it's going to work for 1 or 2 generations, maybe no more.
As far as I know, for at least on the metals, which is just as important as the transistor, which I agree is a lot more, time and effort, but since they've gone to copper and dual damascene, 90 nanometers was 900 nanometers per pitch, and 45 nanometers, 140 nanometers pitch. That's pitch on contact. So that actually is area. So the metals are scaling. We are definitely having trouble with transistors.
Gate oxide thickness.
But again,
gate oxide thickness is not moved, and gate oxide thickness is voltage,
from
and
my
that's power, and
perspective,
it's not scaling.
I worry more about metals for density than the transistor oxide. So if they want to do tricks there, that's fine.
When 3D is free, then you won't ever use another technology.
Okay, Dave.
I'm glad the panel is engaged. So just as an outsider, it sure sounds to me like ASICs are completely broken and dead. I don't know if I can get all the arguments together, but the mass costs have gone way up. Right?
No, it's not mass cost, it's design cost.
Okay, well, the design costs have gone way up in part because there's no reuse. But I think one of the reasons there's no reuse is the number of ASICs starts. Last time I looked, the ASIC starts were on the sharp drop, right? So there's fewer people doing it. The CAD industry is this terrible investment, right? Nobody wants to invest in CAD. So to get the leverage that Mark's talking about, which kind of makes sense, somebody has to build CAD tools, but why in the world would you ever start building CAD tools for the shrinking industry? So I just don't understand the argument. I can see the argument why ASICs are disappearing. I don't know if what TI does is an ASIC. I don't know if a company like TI builds something that's selling, I don't know how many millions of units. What?
And it's hundreds of millions of units.
Hundreds of millions of units. Yeah, so hundreds of millions of units. That's a really cool chip. I don't know if that's what people used to think of as an ASIC. I thought that the idea of ASIC used to be, well, you quickly put something together that wasn't what Intel could do, but it had a lot of advantages in the marketplace, right? Mm-hmm. It sounds like you guys are making a pretty strong argument that is going away. That is just, that's probably some kind of inflection point. It sounded like you're making an argument that, boy, there's some really exciting chips that people who can still make them are making, but the way you figure out how to use them is primarily software. Right. FPGAs are a separate category. FPGAs are kind of like DRAM. As scaling or whatever goes on, we can take advantage of technology. We can make them. We have a marketplace to do that.
But the FPGA is replacing the companies that you're talking about, right?
Yeah, FPGAs with the cost of ASICs and FPGAs and maybe GPUs and other things With software, it's hard for me, except for nostalgia or something, to come up with a reason why ASICs remain viable over the next 5 years.
So let me try to explain to you why you should be sorry. You should mourn the loss of ASICs. I agree with all the comments you made. They are dying. And they're dying because they're very expensive, so in order to build them, you have to have a very large market. If you have a very large market, you don't call it an ASIC anymore. You use the same design technology, you call it a standard product. The problem is that lots of technology that we think about today as being useful standard products, things like graphics processors or media processors or lots of other things, were started by a group of people who built an ASIC to demonstrate a new industry. And at the time, the investment that they needed to do that was not large. They actually demonstrated something that was better than everybody else could do, and therefore built an environment that became NVIDIA or lots of other people who were there and died, S3 and other things. So if we don't have the ability to do that, it says that innovation in the hardware front will be different. So I would argue that it might be wise for us to think about, could we imagine a design methodology that would allow us to enable people to create compelling silicon? Not ASICs, not the same way we do it. In fact, a lot more like coding an application processor, because it's the only thing that's going to be cost effective. But can we enable someone who codes an application processor to potentially get something that would be better than actually coding an existing piece of silicon, if they choose, right? Because I think that might enable a new group of innovation. Might not, but might.
Yeah, I'd say, I think that's possible. It's also could just be our own kind of, it's like I see when a bunch of faculty retire, I'll retire, but hire somebody just like me. I did Joseph Junctions, hire a Joseph Junction guy. Well, that might not be the right investment for the university, right? So I think we have this feeling, warm, fuzzy feeling about our hardware, and that, boy, if we stop doing that, that goes away. But it may be technologically, in the 21st century, that really doesn't make sense. Maybe the thing that replaces ASICs really is software on all these amazing things that you have to sell at least 100 million of to be technically viable. I'd be sad if that's true, but I just don't, except for emotion, I don't understand the argument for it. If someone could, because I think to do this, Mark, we have to invent a new way to fab things. Packaging might be the way to fab things.
I think picking up on Mark's argument, just maybe you got to think about coming at it a different way, right? If we were at a technology inflection point, because we're still getting from the tricks, not scaling. We're still getting a fair amount from technology.
But we is
let me finish.
IBM and Intel, right?
Yeah, but everybody else is still using it. I mean, you still got TSMC making 65 nanometer, 45 nanometer. But the key point is if IBM and Intel, and we actually do have these general purpose processors flatten out, then the market value and the market draw for some of this stuff that Mark's describing will increase, because people still want 2x every 18 months. And you may have to get it for more application-specific type stuff. That's the one inflection point to noodle on real hard, because the performance has still got to come. It's just going to have to keep coming from different sources. And so it's not clear how it's going to be. It may be that we'll get it all by scaling out general purpose processors, but maybe not.
I'll shut up after this, but I think we have to get down to something that costs a couple of $1 million. I think that was probably what the costs were.
I don't think that's a bad thought.
When Jensen and those guys did that, it was at a couple $1 million they could do something interesting. So I'm pretty sure we can do that with software on the really novel hardware devices other people make. Maybe there's some way we can figure out how to manufacture something in small volumes for a couple $1 million. But it'd be a really interesting research project. I just don't know if there's what the business technology to implement that.
So let me just say I completely agree. So basically, I believe technology is maturing in many ways, and our goal now is to be able to leverage the amazing technology we have to actually solve application and user needs. And the most effective way to do that is often to leverage existing things in small systems. So you put the chips together. That's what I was talking about before. I think that is the most important to teach people, to be able to understand a problem well enough and be able to read technology and be able to use that technology. So I'm completely with you. I just am not so willing to basically sell at architecture maybe as quickly as you are. I think the people, when they do that...
You're not willing to be a trader like I am.
Yeah, well, yeah. I figured, you know, that's a great
No,
line.
I want to, you know.
So
I'm looking for this way out, right?
So,
oh yeah, this novel packaging thing. We can make 100 of them.
So look. Right now, design cost is over an order of magnitude greater than manufacturing cost. If we could figure out a way of designing the things, right, that would drop the design cost over $1 million, which is what I think is the interesting research right now, then we should start thinking about fabrication. But people who are working on the fabrication first, they're working on the wrong side of the problem. So I think the real issue is, if I gave this person who had these tools the ability to put them together, could I also give them the ability to noodle on some of the hardware to see if there's something they could do that really makes a difference, order of magnitude, because otherwise it's a non-starter. I think allowing them to do that exploration is useful. If we find people who can do things and get order of magnitude savings, I think there's probably a market for making it happen.
So just going to interject here. So Mark, better design tools would be great, more reuse would be great. Do you think the IP industry will ever start making money in this scenario?
Yeah, so the whole thing is, people basically view this as a CAD business. I don't view this as a CAD business, right? So I view this as someone's building, the way this is going to happen is somebody, AKA NVIDIA, builds a lot of graphics processors. You know, the most amazing thing that Jensen didn't talk about is the whole design process they have at NVIDIA, because they have one of the most efficient design processes around, and they've done it because they build a lot of these units. And so they can build these things, which are very expensive, very complicated, in less money than most other people can. So I'm just saying, for people who are building these kind of standard products, right? He built the previous OMAP, he's building this OMAP. I think he's building the next OMAP. One of the things that those companies will do is they'll start thinking about, well, gee, I'm basically building the same thing over and over again. How do I reuse a lot of the stuff I did last time so my next spin doesn't cost me as much? And those are the people who have the knowledge and the expertise to basically build these kinds of systems. And what they'll then do is, if they're successful, they'll allow a customer to say, well, you don't like what I produced? Tweak some things, pay me a couple $1 million, and you can fab your own, do the qual, whatever, right? But that's the way it's going to happen. It's not going to happen by some independent CAD tool, because the investment they would have to make and the knowledge they'd have to have is way too large.
Hi, I just wanted to be clear about something.
Name and affiliation, please.
Oh, John Delaney. You guys are optimistic about demand, right?
Yes.
Absolutely. People are not computing less.
All right, so there is money to make all of this stuff happen, right?
Yes.
Okay, thank you.
So, Ruby Lee from Princeton University. So I wanted to respond to Dave's
We can go. There's a chair up here for you.
There's so many ways that we can innovate. So let's think for a moment some of the changes in the past. For example, word processing and now self-publishing. Okay, so what if one day you had personal fabs on your desktop? I mean, in the days of Krste, when you said supercomputer on your desktop sounds impossible. But what if you had a fab in your garage or a fab in your desktop, and you weren't trying to build chips that had more and more billions of transistors, but what if you had throwaway chips? I mean, if you build chips that had fewer transistors and cost about a piece of paper, okay? You could do lots of very innovative things. And it's just that we need to stop thinking more of the same good thing is better. Okay, remember when we thought about pipelines? Pipelines is a very good thing. But when we went to 50 stages and 100 stages, that was too much of a good thing. And when we're thinking of cores, maybe certain number of parallel cores is good, but when we're thinking about too many cores, maybe it's not necessary and it makes the chip cost more and so forth. So just think out of the box a bit and go to fewer transistors, fab on your desktop, anyone can do it. It's possible. We just need the imagination.
So I'll comment there. What we build is a consumer device, and the consumer, for whatever reason, when he sees 120 hertz, 1080p video, it looks better. And if you've seen it compared with 60, much less 30. So if you start going down to things that a consumer actually wants, that stuff, there's 2x, 4x hardware, just hard stop. You can just, you're just using the same compression algorithm, but you're having to do it a lot faster, and you throw transistors at the problem. And that's most of what the application processors around are doing stuff much better in image, video, graphics, display, audio, all those things, and just general purpose. You're doing a web browser, I want it, instantaneously to flash up. Nobody wants stuff slower. Everyone wants stuff cheaper. And everyone wants new and beautiful widgets. So that's kind of the trap we're in. I mean, the thing that's a transition or difficult for us is do all that and make it the same cost or cheaper in 2 years. It's just kind of a crazy treadmill. But consumers want this stuff. They don't want stuff that's as no better or worse than what they did a couple years ago, and it just costs a lot.
Maybe I would like to make a comment on a remark of innovation. If you're looking for like a sweet spot, which is then away from the $60 million investment and so on, maybe the more than more area is where it will happen. We also see, of course, a lot of electronics companies and system companies who are trying to combine like an advanced chip you can make, right, in CMOS with this special thing, an idea, a functionality you build on top. And then, of course, you can be creative, and also that doesn't cost like that much amount of money. You can have a kind of project with a nice MEMS device or a bio project, and in terms of functionality, in terms of IP, it can be very interesting. So there is a lot of areas that are open, and the application areas are huge. But that area is still, I would not say embryonical. The technologies are there. It's not about, but still, it's wide open. A lot of things can happen there.
I think though that I went to the IMEC roadshow ARM meetings last year, and one thing that was as a comparison point is the human brain, which is if you talk about complexity, we're still not close to the human brain in complexity, and so people still want devices with that kind of complexity. And so, your cell phone, billion transistor chips in a cell phone is still, people actually want that. So going to a simpler technology, if consumers would reduce their requirement and go back to, pen and paper, maybe we could go the same way, but it doesn't seem the world's that way.
I think what Ruby was really talking about is the more than more thing, which is, we have tremendously capable technology. If we could do some other things that we can't do right now, that will enable really interesting end applications, right? So some new kind of transducer or sensor or whatever, there you can merge that with a little bit of smarts or a lot of smarts, because a lot of smarts cost nothing, and you can do amazing things. So
I was thinking of two technologies. One of my colleagues at Princeton talks about large area throwaway electronics. Mm-hmm. Okay, I mean, if you could have a chip for as cheap as a piece of paper, mm-hmm. and you throw it away, I mean, you could do lots of interesting things.
That's ongoing. It's an existing technology. Well, still.
But this doesn't negate the fact that some things you still want to go denser and denser. Yeah.
It's large scale. It's
right.
Organic electronics on foil.
Right.
Yeah.
I mean, think of a 1 cent IC, that you can do yourself. The
It's
other technology I was thinking of is a colleague at HP much long ago, maybe 15 years ago, was building this desktop fab. I mean, it never went anywhere, but imagine if you had a desktop fab that you could produce not a billion transistor chip, but maybe 100,000 transistors or something. You just whip it out. I mean, that would be really interesting.
I thought Xilinx sold those.
What?
I was going to say, I thought Xilinx sold those.
Yeah, that's what I thought. I thought it was a Xilinx programmer. Yeah.
I would also like to comment like the bioelectronics area. If you're just in that area, a lot of innovative things there, and it can combine also high functionality chips sometimes. It's not, you can combine older technologies, but in some cases you need a high level of scaling, high integration density, very big challenges on packaging, and combination with like another functionality like connection with a biomolecule or with a sensor or an actuator.
Hi, Roger Doring, CSU East Bay. It used to be that we would build our ASICs for higher performance than we could achieve with the general purpose processor. I was talking recently with a colleague of mine from Berkeley who has a company up there, and he builds vision chips. And he recently ran a simulation on a processor, a GPU, that ran faster than his ASIC. So it's become pretty clear that we're no longer building ASICs for performance, but would you say that would you make the statement that it's fair to say that we could be building ASICs for power?
I would say one example does not make a rule. So, so it is true that there are some things that you can do very effectively on these very parallel, very high throughput machines like GPUs, but there are many applications where a GPU might be able to do image compression, for example, faster than an ASIC, but it wouldn't do it within the power budget of the ASIC. So I think, in my view, the name of the game moving forward is computational efficiency, because I think everything's sort of limited by power envelopes these days. And if you really want to get higher performance, you have to make it more efficient, because whatever you're doing is already at the power envelope. So in some sense, higher performance means higher efficiency. You couldn't put a GPU in a handheld camera, because just you couldn't get the heat out, you couldn't get the energy in, just a whole bunch of stuff like that.
So I think there's also an argument on this power density issue that people tend to forget. They think that, we're moving into 45, 32, 22 nanometer technology, and that leakage and power is a big problem, which I'm not pretending it isn't, but it's still power density or power. What was your term again? I'm sorry. The computational energy is still improved when you go to that next generation. In that you do still gain a lot from the physical dimensional scaling, even if your transistor itself is not such a great switch.
Right. Well, you win because the energy to do each operation when you scale by a factor of 2 scales by a factor of 2. The problem is that you get 4 times as much gates per square millimeter. So you have a factor of 2 savings in energy per operation, but you get 4 times as many ops per second if you wanted to. So that's why you're power limited. That's why you're power limited. It's not that it's worse going to the new technology. It's better, but it's not as better as it used to be.
Okay, so I think at this point we're getting close to wrapping up the panel. I just was thinking when I'm sitting here that there was this famous movie where a recent graduate was given the advice, plastics. So I'm going to go down the panel and ask you, for the new graduates in the audience, what's your 1 or 2 or 3 word summary of where they should be looking past this technology inflection point? Brad.
Plastics.
It's all ball bearings these days. Looking forward, I think it is the technology inflection point is that we're shifting more and more from what's in the transistors, what's in the sand, what's in the copper, to what's in the design, what's in the architecture, what's in the system architecture. I think the most valuable people that we will find in the next 10 years will be people that can cross the hardware-software boundary. We always seek those people out now, because it's going to be the next clever solution that's going to go ahead and get us onto a different computational energy curve or a different power performance curve or whatever, will probably be a solution that crosses the hardware-software boundary. We call them appliances these days, and there's a very, very, very good business. If you got a going appliance business right now, you're doing a pretty good thing. And those are all solutions that cross the hardware-software boundary.
So Brad says washing machines. Okay.
Ball bearings. It was ball bearings. That's a line from
Mark.
Fletcher.
So I think it's all about solving application problems. And my word would be embedded systems, son, embedded systems.
Dave?
You want one final comment? Is that?
You had to come on plastics or something.
Oh God. I suppose my final comment is I hope we don't run into a roadblock where scaling stops just because there's so many fascinating, innovative things we can go off and build, and it's fun being part of that. So if somebody said, stop the number of transistors, stop where you are, and try and find and do something very different with a fixed budget, I think that's time to go off and start up a bait shop or something, but not this.
So, I think we should be careful not to judge the local economic environment in this previous year as a predictor of the doom of the semiconductor industry. I think there's still a lot of, even in a bad year, there's still $200 billion of revenue in the semiconductor business. So there's plenty of money to drive innovation. Definitely, it's going to be tough going forward to, some below 10 nanometers, maybe things start to get tough, but I still think there's plenty of room for innovation. I agree that I think if you wanted to look for a career in the future, the systems design, system integration place is where the skills are going to be needed.
One boring and one sexy. The boring one is EUV technology, which is technology, but I expect if this breaks through, it might have big impacts on the industry, the companies that are doing, and again on the possible innovations, because it's really an enabling technology. The more sexy one is just bioelectronics, because in my imagination you have so much very nice applications for the people and so on. So there I also expect a lot.
Okay, well, let's thank the panel for a really interesting session.